Hi all, I'm Satwik. Me and my teammates Deril and Sukanya are going to present on our final project, exploring Bloom filters for username validation in large-scale systems. So, so let me give you a brief idea about this project. Companies like Instagram, Reddit, Twitter, etc., face the challenge of quickly checking the availability of usernames among millions of registered users. Traditional approaches like linear search are highly inefficient for such large-scale systems. Binary search, on the other hand, offers improvement but still requires multiple steps to find a match. So there lies a solution in using Bloom filters. It's a space-efficient data structure that efficiently checks username availability without iterating through all the registered usernames. So what is a Bloom filter? A Bloom filter is a space-efficient probabilistic data structure used to test set membership, determining if an element is likely present in a given set. It requires minimal memory compared to traditional data structures, because it uses something called bit array, making it ideal for large-scale systems with a massive number of elements. Due to its probabilistic nature, there is a possibility of false positives, meaning it may incorrectly suggest that an element is already a part of the set. A Bloom filter guarantees no false negative, meaning it ensures that it never reports that an element is not in the set, providing a high recall rate. The next section is about the implementation of Bloom filter. This will be continued by Sukanya.
So I'm going to go over the implementation of Bloom filter. So in the context of Bloom filters, it's essential to choose a reliable and well-distributed hash function. This is important because a good hash function can minimize the probabilities of collisions. The more evenly the hash function can distribute data across the array, the lower the chances of false positives. The next is bit array initialization. So when initializing a Bloom filter, we create a bit array of a certain size to store the membership status of elements. The size of this bit array is typically determined by the expected number of elements to be stored in the filter, as well as the desired false positive rates. Then there's element insertion. So when an element is added to the Bloom filter, the selected hash function is applied to the element. The output of the hash function, which is an integer, is used as the index of the bit array, and the bit at this index is then set to 1. If multiple hash functions are used, this process is repeated for each hash function, each time setting a different bit to 1. Then we have element query. So to check if an element is in the Bloom filter, we apply the same hash function or functions to the element and check the bit at the corresponding index in the bit array. If any of the bits checked are 0, then the element is definitely not in the filter. However, if all the bits are 1, then the element might be in the filter, or it could be a false positive as well. We have then false positive handling. It's a limitation of Bloom filters because there's always a possibility of false positives, which is when the filter incorrectly indicates that an element is present. False positives occur because different elements may have the same hash values, causing their bits to overlap in the bit array. To manage this, the size of bit array can be increased, or the number of hash functions can be adjusted. Larger bit arrays and more hash functions can decrease the probability of false positives, but they also increase the computational and space cost. So therefore, there must be a balance that must be struck to achieve the desired false positive rates for the specific use case. We go over to the next slide. So here we have a flow chart for our user validation system. So we start the process and we check. So the next is we check whether an element E is a member in the set S or not. Let's say a client asks or a user asks the Bloom filter whether the particular element, which is in our case a username, is a part of this set S or database. So next, the Bloom filter checks if the element is present. If it's present, the process moves to the next step. If it's not in the Bloom filter, the process ends and returns a no. This is a true negative, meaning the element is correctly identified as not being in the set. Then there's check the existence of the element E in the database. If Bloom filter indicates that the element may be in the set, the system checks the actual database or the set S to verify. If the element exists in the database, the process ends and returns a yes. This is a true positive, meaning the element is correctly identified as being in the set. If it's no, that is, if the element does not exist in the database, the process ends and returns a no. This is a false positive, meaning that the element was incorrectly identified as being in the set by the Bloom filter. And the term overhead here refers to the additional computation work or resources required to check the actual database when the Bloom filter indicates an element might be in the set. Thank you. I give it to Deril now. He's going to handle the rest of the presentation.
Going with the demo, we have a Bloom filter implementation written in Python here. We chose to write it in Python so as to make use of inbuilt hashing libraries which different communities offer. We have a class Bloom filter here which takes in a CSV file which mimics the database today. So if we open ip.csv, this is the database which we have. We have 3 usernames already pre-fed into the database, and this data set is fed into the Python file along with the particular hash function which we want to use, and we get the result out. So to demo it, if I run this file, if I run python bloom.py, we input the CSV file, and let's say we want to use the mms3 hash function. After this, yeah, so now the code prompts for a username to check. So if I give some username which is already existing in the database, let's say my name itself, it will say that username might be in the database. This is what Bloom filter is expected to do. And hereafter, the username is again asked to enter another username. So if I give Andrew 1998, it says the username was not in the database previously, so it will be added now, and the program exits. And as we can see in the CSV file, the new username has been added. So this was a simple demo of the Bloom filter which we have implemented. Going back to analysis, we did a certain time and space complexity analysis on the entire code which we have written. So since Bloom filters make use of multiple hash functions to avoid collisions, we have a time complexity of O of k, where k is the number of hash functions implemented. The more the hash functions, the less the collisions there is. And when it comes to space complexity, like Sukanya discussed about the bit array, whatever the bit array size we are choosing to implement, that would be the space complexity, and that's the only space which we'll be using. And just an additional step, we have used multiple hash functions in Bloom filter so as to avoid collisions. And going to conclusion, like Satwik and Sukanya discussed, Bloom filters offers a space efficient and fast solution, not just for username validation, but we can extend the use case for multiple different scenarios like email verification, password verification, etc. And since the lookup time depends solely on the number of hash functions, which is O of k, we can say that it is almost a constant time lookup for handling high volume data sets efficiently. Although Bloom filters may produce false positive, which there is a fail-safe mechanism, we can for sure say that there won't be any false negatives. Thus, for scenarios wherein we want to say that the password doesn't exist in the database or there's a weak password in the database, we can always rely on Bloom filters for it to work. And regarding the fail-safe mechanism, we can always have a, like Sukanya discussed in the flowchart, we can always have a binary search implementation in the backend to complete the application entirely. And thus, by implementing Bloom filters, companies can make use of this to enhance the user experience, because we can find out if there is a username existing in the database in very less time. Thus, we can give a quick response back to the user. And that is our project. Thank you.